quiero agradecer de corazón que estéis todos aquí. Hoy es un honor para la Universidad de Almería y un privilegio contar con la presencia del Reinhard Genzel entre nosotros, para aquí compartir con nosotros su conocimiento, su experiencia. Como todos sabéis, el doctor Genzel es reconocido a nivel mundial al ser galardonado con el PREMIO NOBEL de FÍSICA en el año 2020, junto al británico Roger Penrose y la estadounidense Andrea Ghez, por su hallazgo sobre los agujeros negros, especialmente por el descubrimiento de un objeto compacto supermasivo en el centro de nuestra galaxia. Reinhard Genzel estudió física en la Universidad de Friburgo y en la Universidad de Bonn, donde realizó su doctorado en 1978 en el Instituto Max Planck sobre radioastronomía. Entre el año 1978 y 1980 estuvo en Estados Unidos, donde fue becario postdoctoral en el Centro Harvard Smithsonian de Astrofísica en Cambridge, y del 80 al 82 fue becario de la Miller, ¿no? la prestigiosa beca Miller de la Universidad de California en Berkeley, trabajando sobre espectroscopía de infrarrojo lejano. Posteriormente regresó a Alemania, a Múnich, Baviera, donde es profesor honorario desde 1988, y en 1999 fue nombrado profesor titular de la Universidad de California en Berkeley. Es miembro científico de la Sociedad Max Planck desde 1986 y director del Instituto Max Planck de Física Extraterrestre en Garching, en Baviera. Miembro de la Academia Europea de la Ciencia y de la Academia Alemana de las Ciencias Naturales, entre otras instituciones. Sus investigaciones se han centrado en los agujeros negros masivos y la formación de estrellas dentro de la galaxia, así como la formación y evolución de la galaxia, que estudia con espectroscopía de infrarrojos, submilimétrica y milimétrica, con imagen de alta resolución, así como aplicando interferometría espacial. Ha sido el primer astrofísico que centró su estudio en seguir el movimiento de la estrella del centro de la Vía Láctea y consiguió demostrar que éstas orbitaban alrededor de un objeto muy masivo. Finalmente se descubrió que dicho objeto, de densidad enorme, era un agujero negro de unas 4 millones de masas del Sol, y que ahora se ha bautizado ese agujero negro como Sagitario A. Por sus investigaciones, el profesor Genzel ha recibido muchos honores y premios, entre ellos la medalla de oro, la medalla Otto Hahn de la Sociedad Max Planck, la prestigiosa beca Miller, como he comentado anteriormente, de la Universidad de California en Berkeley, el premio Tycho Brahe de la Sociedad Astronómica Europea en 2012 y la medalla Genzel de la Real Sociedad Astronómica Británica en 2014, y además diversos doctorados honoris causa. Bien, hecha esta introducción, repitiendo el honor de tener aquí con nosotros al doctor Genzel, pues le paso directamente la palabra para que nos vaya hablando un poco de su experiencia. Dr. Genzel, the floor is yours.
Wow, now you had to listen to all of this, what I've done in my life. Yeah. Well, most of you are students, I suppose, and who's in physics? Chemistry. Mathematics. Okay. Oh, well, here are the brains. Very good.
John, please.
John,
Press here. You want to use the microphone?
Bueno,
Mic. Yes.
sí, no oigo.
Press. Press.
A
To the red light. Yes, green light.
Ah, ya. Luz verde, vale. Ok, está bien. Bueno, nada, mi cuesta de traducir, y si no aprieto el botón verde no voy a poder traducir, pero ya estoy listo.
All right, so look, let me introduce myself in a slightly different way. So I'm a I'm a failure because a real failure because I wanted to, when I was young, become a star in the Olympic Games in Munich and throw javelin. And I was in the selection team for Munich. But in the end I didn't make it because my elbow broke. So I had to give up.
And what sport was that, sorry?
Javelin throwing.
Él dice que ha sido un fracaso porque su ideal era ser miembro del equipo olímpico de Alemania en jabalina y estaba en el proceso de selección para los Juegos de München, pero no entró.
Yeah, okay, so that career having crashed, I then changed over to something which is equally difficult, but I knew a lot from my father, who was a physicist, so I started to study physics. The idea to become an astronomer came later.
Pues entonces no entraron en los Juegos, decidió hacer otra cosa y algo que había aprendido mucho de su padre, que era físico. Entonces optó por estudiar física y la astronomía llegó más tarde.
Now, in my generation, growing up in Germany actually was not so easy as it is now, because, of course, post-war and all these things which had happened in Germany were still very present. So it was obvious that the way to go was to go to the United States, and so this is what I did. And I was extremely lucky to find there support and mentors and places where I could work. It was fascinating. In particular, in Berkeley, I fulfilled a dream of mine to work with a very great physicist, Charlie Towns, who received the Nobel Prize for the invention of the laser on the maser, and he became sort of my second father.
Pues en su época no era tan fácil progresar en Alemania, no estaba tan lejos de la Segunda Guerra Mundial y todo lo que implicaba, con lo cual optó por ir a Estados Unidos. Y fue a la Universidad de California en Berkeley y tuvo la suerte de encontrar allí como mentor a Charles Towns, que era Nobel de Física por su invento del láser y máser, y lo que no dijo es que Charles Towns vino a hablar en las Jornadas Astronómicas de Almería. ¿En qué año, Pedro?
2009 creo.
2009. Something like that. He came to talk to us in 2009.
Yeah, no, I mean, that's when my career started really as an experimental astrophysicist. So I learned how to build instruments and then use them initially for the so-called far infrared wavelengths which you cannot do from the ground. So we flew in an aircraft of NASA, the Kuiper Airborne Observatory, and basically did molecular and atomic spectroscopy in very long wavelengths.
Entonces, construía instrumentos para observar en el infrarrojo, o sea, espectrógrafos en el infrarrojo muy lejano. Y estos no se pueden observar desde el suelo, entonces tenían que volar en un avión de la NASA, el observatorio Kuiper en el avión, y eso es lo que siguió con Charles Towns.
So let me tell you then a little bit about why I fell in love with black holes. So you see, black holes, and I'll discuss this in my talk tonight, are things which come out of Einstein's theory of general relativity. And they're fairly obvious. It's pretty simple, actually. And have a lot to do with the fact that photons or light also sees gravity. You know about gravity, right? You jump up and you come down. No way you fly into space. And if you make the Earth, gravitationally more attractive than it is now, then even light cannot escape. So then we are in a black hole. It's very simple.
Bueno, porque se enamoró de los agujeros negros. Son predicciones de Einstein, velocidad general, y son muy simples, realmente. Se trata de los fotones que se atraen por gravedad. Sabemos si saltamos en la Tierra, no saltamos al espacio, porque la Tierra nos atrae de nuevo, y si la Tierra es un agujero negro, ni la luz podría escapar.
Right, so in the 1960s, actually, so about 60 years after Einstein's, or 50 years after Einstein's predictions, the first candidate black holes were discovered by astronomy. X-ray sources on the one hand, and then the so-called quasars, very powerful radio emitting sources, but very, very distant. And if you convert then the amount of radiation you see, it's enormous because of the distance dimming the light. And so theorists in the 1960s had to really think about very hard, how could you generate so much radiation? And the answer is very simple: black holes.
Pues en los años 60 del siglo pasado se descubrieron fuentes de rayos X, que eran estrellas por un lado y cuásares por otro. Y se puede calcular que la cantidad de energía saliendo era enorme. Y los teóricos se preguntan, ¿cómo pueden generar tanta energía? Y la respuesta resulta ser simple: agujeros negros.
Yeah, if you want to know more about this, again, tonight would be an occasion. Don't want to take too much of your time. So, by the 1970s, Towns and I was then part of this team, then became faculty member. We started really making observations in the nearest galaxy center, our own. And that seemed to be the right place where you might see the motions of stuff. And motions is the way to measure gravity. Even if it doesn't radiate, the motions is what makes things change position, and then you can make statements about the concentration of mass. And so by the mid-80s, we actually had pretty good evidence that there might be something. But you see, it took another almost 40 years from then to where we are now. So sometimes you have to have patience, really patience. You have to be excited about things. Do what excites you.
Pues él empezó a trabajar en los años 80 con Towns, y buscando estrellas cerca del centro de nuestra galaxia, pensando que sus movimientos podrían delatar la presencia de un agujero negro en el centro. Y casi habían llegado a encontrar uno, pero al final ha tardado 40 años más. Y entonces él dice que lo que hace falta es mucha paciencia. Y para sostener la paciencia, emoción. Hay que hacer lo que te emociona.
Yeah.
Thank you very much, Dr. Genzel, for your talk. And now it's time for questions from the audience. And I think that many people have a lot of questions because it's very new for us to have a Nobel Prize here with us.
Good morning. Hello, Mr. Genzel. I'm Chema. It is a pleasure for me to be here. Well, I have a question for you. It is, do you think we will be able to observe directly an extrasolar planet with a telescope in the future?
We are already doing it now. We don't need the future. No, I think it's very clear that observing extrasolar planets is something which we can do now. In fact, with the same instrument we are using for the black hole in the galactic center, you just have to have high precision imaging. Okay. Perhaps the more difficult thing, though, is to measure what's happening on the surfaces of those extrasolar planets. And the particular issue there is the chemistry in atmospheres. We know that a number of these bigger extrasolar planets, and we know it by now, about 5,000, I believe, of them, have atmospheres. But the question, of course, we would like to know is how does it work? And of course, at the back of our mind, being human beings, we think, are there things like Earth, right? I mean, that's the most obvious thing. Maybe the wrong question, you know, it's never always being egocentric or humanocentric may be the wrong thing, but that's what will happen in the next 20 years, without any doubt, that we will measure the chemical constituency as well as reactions on exoplanets.
Thank you.
Hello, thank you so much for being here. I think it's a great pleasure. I am working in a different field, in biomedicine basically, but I would like to know, in your thoughts, what does it take to a researcher to make a great discovery that can change human society, as you have done?
Well, I mean, first of all, let me say is I'm certainly using this honor which I've had to tell young people, hey, this is something you might want to do as well. And also to tell our societies, look, only if you are curious and if you're willing to do the impossible will we make progress, right? You know that we have many problems to solve. Right now seems like a mountain of problems on Earth. Why? Who has ordered this? But for sure, by doing research, then of course developing technology in the process, we may be able to solve a number of these problems. So it's a cycle. It's a cycle of curiosity-driven basic research leading to technology, leading to solution of problems. It is very important for all of us to realize that to turn that around is often not possible. And many politicians believe it can. They say, why don't you stop this black hole stuff? It's not that important to us. You know, who cares about black holes? Why don't you develop a new car, a new aircraft, or whatever, solve the climate crisis? The answer is, if you look at towns, those Charlie towns we talked about, the laser nowadays is known to every one of you for its uses in industry, for its uses in medicine, for its uses as the most precise time clock we have available, to actually allow our cars to drive through this GPS and so forth. Yet Towns was absolutely not interested when he did his work in developing a technology tool. He just needed a lamp to look in the 5 infrared millimeter range to look at and understand molecules. Okay? So the curiosity about molecules drove Towns to develop initially the maser, so the long wavelength part of it, and later on that turned into the laser. Okay? So it cannot be easily turned around.
Thank you so much.
Creo que no hace falta traducir porque todo el mundo sonríe, que presumiblemente significa que entiende. Pero es cierto que el láser tarda muchos años de todas formas en utilizarse. Los descubrimientos de la ciencia pura a veces no es obvio lo que hacen. Se refería al láser como una solución buscando un problema, pero al final todo el mundo sabe lo útil que es y lo inútil que parecía cuando lo descubrieron. Okay.
Another example, by the way, is in medical applications is both nuclear resonance techniques, but also observation, subcutaneous measurements with infrared techniques I'm using. So the techniques, the detectors and the spectroscopy, which we are developing, can immediately be used without any invasive procedures to go and check, you know, whatever is happening below the skin of a person.
El infrarrojo que se desarrolló para la astronomía se puede usar en la medicina para investigar la tejido subcutáneo.
Hello, Dr. Genzel. It's a pleasure meeting. I wanted to ask you what's your opinion about the observatory in Canada, because nowadays we have several telescopes much bigger and better in the world, so can it still give relevant results?
Right, now you should know that my group and I actually were developing, or rather putting into operation, two major instruments which are now known to be pretty revolutionary on Palo Alto in the 1990s. One of them was what we call an integral field spectrometer. You see, spectroscopy is something where you have light coming at you, and then you disperse the light, and typically, you know, you would use a grating spectrometer, but then you lose the second dimension for imaging. And so if you want to do both imaging and spectroscopy, you have to do something, and that's what we call integral field spectroscopy. And our first integral field spectrometer we tested out on Palo Alto. Okay, so that was a very important opportunity to make that test. The second instrument we built is what now almost all big telescopes are using to correct the Earth atmosphere, and that's called laser guide star adaptive optics. So we're shooting lasers in the upper atmosphere, get backscattering, and then use that backscattered radiation to correct the distortions by the Earth atmosphere. So that was in the 1990s, but it was clear to us, at least at the time, for the goals we wanted, namely distant galaxies, black holes, high resolution, that we needed a bigger telescope. And indeed, ESO was at that, European Southern Observatory, ESO at that time, were just about to put into operation the first of the BLTs, 8-meter class telescope. And so it was clear that the 3-4-meter class telescope, which we had been using up to that point, would not be sufficient anymore. Nowadays, I would go even one step further. We are using ESO's 4 8-meter telescopes simultaneously as a big 200-meter telescope, so to speak. And so it is necessary to do this in international collaboration, and it is necessary to go to the best site in the world, which is Chile. And so while Palo Alto was great, really great for a number of years, it was clear to Europe, including Spain, that certainly these very big telescope applications would happen to have happened to play in Chile.
Bueno, no voy a traducir, pero voy a añadir que el mejor sitio del mundo para la astronomía es Chile y también La Palma, que está en España.
Well, we worked in La Palma also, so I mean.
Muchísimas gracias por la charla. Yo quiero hacerle dos preguntas que pueden parecer tontas, pero quiero hacérselas. En las jornadas astronómicas que hemos estado haciendo hace muchos años, hemos escuchado, gracias a Dios, a muchos premios Nobel, como usted, y todos han coincidido que se iban a Berkeley, a Harvard, a las grandes universidades de Estados Unidos, para precisamente eso, para ganar un Nobel, para ser... Pero mi pregunta es la siguiente: ¿un joven de Almería como esto, trabajando duro, puede ganar el Nobel aquí en Almería? Y segunda pregunta: es maravilloso todo lo que habla sobre los agujeros negros y todo lo que gusta la astrofísica, maravilloso. Usted como Nobel, como persona de relevancia científica internacional, ¿tiene remedio nuestro planeta con todo lo que yo lo que tiene? O sea, ¿tiene remedio? Porque nuestro planeta avanza a un problema muy serio. Ya estamos aquí. Muchas gracias.
So he said, if somebody from Almería manages to get to a university such as Berkeley, could they get a Nobel Prize?
In Almería?
No, if somebody from Almería who goes to Berkeley to study a university like Berkeley.
I think
without going.
I don't. I
That's the
think
question.
I would say the answer is not necessarily anymore having to go to Berkeley. The answer is Europe.
Mhm.
And that is what I can tell you in astronomy has happened. Certainly not exactly in space. I mean, the James Webb Telescope is still the biggest machinery in space, but on the ground, in optical astronomy, Europe reigns supreme. Because we have decided to work together, put our forces together, our brains together, our young people together, and we have Spaniards coming to us, or Germans going to Spain, and that is the solution to these problems. Viva Europe!
Es que no hace falta ir a Berkeley. Europa ya es mejor. Y para añadir un toque personal, incluso el Reino Unido sigue en el Gran Observatorio Europeo del Sur. Menos mal.
Hay una segunda pregunta.
¿Y la segunda pregunta?
Even the Brits haven't pulled out of Easter.
That's right. That's right.
That's what
That's a very good point. Brexit did not happen in astronomy. The Brits are clever. They stay in Israel.
The second question was if our war has a solution. Especially, I think he's asking for the climate change.
Climate change.
Climate change.
Oh my God. Okay. Oy, oy, oy. John, you want to answer this? Go ahead.
Yeah, no, I'll answer you.
Yeah.
You are the Nobel Prize. You have to answer.
Okay, look, what I would say is clear. There are several factors here involved. One factor is obviously the overproduction of resources of all types, and therefore the production of CO2 in too large amounts. The next one is certainly the number of people we have on Earth. That is less of a problem apparently in Europe right now, but certainly more of a problem elsewhere. There's of course also the inequality of social and welfare being of humanity. All of these issues need to be solved. I am in principle optimistic that using the same route which I mentioned before, technology and etc., can lead to a solution. But please, without wars. Please, no more wars. Please, no more dictators left, right, middle, who play their little game of, I have to be the big man. This is not the time for this.
Ya que se entiende, pero él achaca los problemas no solamente al CO2 en el ambiente producido por la industria, sino la cantidad de gente en el mundo, que es un problema, aunque en Europa en concreto no, pero en el resto del mundo sí. Y él tiene esperanzas en la capacidad humana por tecnología e ingenuidad de superar los problemas, pero por favor sin guerra y sin dictadores que quieren imponer sus horrores sobre el resto.
Hello. First of all, thank you very much for visiting us. It's a real pleasure to have you here. My question is not strictly related to black holes, neither to climate change, for that matter. And is there anyone in your community, in your field, anywhere close to describe in a scientific way what dark matter is? Because it's 20% of matter, and as far as I know, we don't have a clue yet of what it is, and maybe it's a Nobel Prize waiting for that guy.
Yeah, no, there's no doubt. Has been waiting for 40, 50 years, okay? Okay, so dark matter. It's clear that we sense dark matter from just the action of gravity again on other things. And from this we basically calculate how much material there has to be. Then we take what we can definitely see, and there's a lot left over. So that's what you said. So that's number one. Number two, by making a sophisticated set of computer models, which we can now do, we can say, suppose there is this dark matter which only reacts with normal matter through gravity, but not through the other forces, electromagnetic force, etc., etc. How would the universe evolve? And the answer is, if there would be no dark matter, there would be no galaxies. So that's very important to know, because you can calculate, so to speak, from the Big Bang onwards, a universe without dark matter and a universe with dark matter, and you would find that if there's no dark matter, there was not enough time to form galaxies. So from that argument alone, irrespective of what it is, you know already that something is really true about this dark matter story. What is it? Yeah. Well, our particle physics colleagues have been looking harder, still harder, and have not yet found anything. And so if you look in the literature right now, every day, at least 20 papers dealing with that story, and some of them are getting pretty desperate. For instance, some are beginning to propose that it's black holes, which make up dark matter, something which had been looked at initially but then thrown away. It's still possible to find solutions with black holes as dark matter, as long as the black holes are small enough. But no, you are absolutely right, and many people are trying it, and I can't, I'm not a sage, I cannot tell you when the solution comes.
Thank you very much.
Muy rápidamente, el argumento en favor de la materia oscura es que si haces los cálculos del universo al inicio, desde el principio, y no incluyes la materia oscura, las galaxias no se forman. No hay manera de formar galaxias. Entonces es un argumento bastante potente en favor de la materia oscura. Sin embargo, no se encuentra, y los físicos de partículas le están buscando y no lo encuentran. Entonces, así estamos. Pero algo que hace el efecto gravitacional sobre las galaxias tiene que estar de una forma u otra.
Hey, this is Mentor. First of all, thank you to be here. I'm really glad to hear you. I have two different questions. The first of them is, do you think that the scientific focus will change from America and Europe to Asia? And the second question is more personal. Is, do you think that cosmology, what's your personal opinion of cosmology? They have really theory that can support all their results? Or do you think it's more related to theoretical properties that could explain our world?
Oh my God, again, you're calling on me as a sage, which I'm not necessarily the best one at. But will Asia dominate? Asia, that is China, to be sure, already now dominates the number of papers submitted in the scientific journals. That's clear. That has happened over the last few years, so the change is dramatic. Does that mean that they will also change the quality? That they have to show. It's interesting to see that if you maybe, you were probably too young then, but in the 1990s, similar things were said about Japan, at least industrially. And it has not happened really. Why? Because Japan all of a sudden, changed its society and did not grow anymore, despite the fact that they're doing outstanding work in research. They're doing outstanding work in research, but they cannot dominate in that sense. They participate very importantly in some areas, but they don't dominate. In China, I would say, the numbers certainly impressive. I would also say we have a number of Chinese scientists in my own group. These are hardworking young people, very impressive, but they have not learned so much to be independent. They have very much grown up in a society where you get told what to do. And if you want to become an independent scientific mind, doing really revolutionary things, at some point you have to do it without your father. And that they have to show, to me at least. I think it is really true that you cannot run a scientific endeavor like a military army or something like this. So that we have to see. The US, I wouldn't underestimate. The US is right now in a very difficult situation. It breaks my heart because I love America, actually. I've lived so many years, partly in the United States, and to see how much the country has split into two camps is just incredible. And I don't honestly know where it will end. Of course, the greater worry is, will that jump over to us in Europe? I mean, whether we also start splitting into a rural and a city like. Did that answer your question? Sorry, I'm not a sage.
No, bueno, hay mucho ahí. Lo de China, él lo compara con Japón en los años 90, cuando todo el mundo pensaba o decía que Japón iba a dominar la ciencia. Japón no domina la ciencia, pero contribuye bastante, colabora. China ahora publica más publicaciones científicas que ningún otro país. Tiene buenos jóvenes chinos en su grupo ahora. Trabajan bien, son inteligentes, pero él opina que todavía no se fomenta la independencia del pensamiento ahí y que hasta ahora no puedes producir ciencia creativa si todo es jerarquizado.
Back to the question, maybe from you or other. I mean, what about someone from Almería and Berkeley? Do it. Do it. I mean, it has not changed that the top American educational places are top quality. They are and will remain top quality. It's not as easy anymore for them, but they will remain top quality, I'm sure. And getting that experience is also wonderful, just because you see something, a society which is different from your own, and that, at least for me, was a a very important part of my education.
Ha enmendado un poco lo que dijo sobre ir a Berkeley. Él dice que sí, que después de todo Estados Unidos tiene centros de educación los mejores del mundo y que sí vale la pena ir y tener la experiencia y ir a otra sociedad que es diferente de la tuya y eso siempre vale la pena.
Hello, Reinhard. Thank you very much for visiting us here in Almería. I'm a PhD student in Almería, but also a scientist at the German Aerospace Center working in Plataforma Solar de Almería. My question is related to black holes and more precisely to the Hertzsprung-Russell diagram, which classify living stars. Can we classify black holes as dead stars? And if yes, why don't they appear on the diagram?
Can we classify them as
Death stars.
Death stars? No, because I mean the process which leads to what you would call a Death Star is the fact that a massive star, much more massive than the Sun, radiates per second much more of its mass energy than the Sun, and that as a result means it runs out of fusion fuel much earlier. In fact, for a 100 solar mass star, that's only a few million years, at which point radiation is not efficiently or not much produced anymore. As a result, gravity takes over, the thing collapses until the fermions in the system stop the collapse or result in another explosion, which we call a supernova. In any case, at the very end of this, there can be a stable system called a neutron star or a stellar black hole. So that's the picture we have, and that's strongly confirmed by, say, observations of gravitational waves. So it's very clear. We are, I should say, not yet fully in the position to know how broad the spectrum of these types of black holes is. The standard picture had been there would be, say, 8 to 20 solar masses, and now we have, with LIGO, several cases up to 100 solar mass, and so people are speculating, is that the same process or is there a different process or something like this? Apart from this, we have the massive black holes, the ones I'm studying, which sit in the centers of galaxies and are being basically given a round of meal every few days, so to speak, from the galaxy, and sometimes that comes richer and sometimes it comes poorer, and when it becomes very rich, then the thing starts becoming very luminous, becomes a so-called active galactic nucleus and even a quasar. Then in between these, and these are objects from millions of solar masses to about 10 billion of solar masses, approximately 0.5, 0.3% of the mass of the galaxy, and co-evolving with the galaxy, approximately. A big question is now, are there also black holes in the middle between all of this? We don't have any firm evidence, but I'm fairly certain we will have a chance through measurement to do whatever we've done, say in a globular cluster, and that's now possible. It's just a question of using the instrumentation and time. It takes time to make the measurements, but otherwise it's possible. So black hole research in many ways is going to be an exciting field, because for one thing, are there really the black holes which Einstein's theory told us about? What about the central singularity, which Einstein's theory predicts, which most of us feel cannot be right? But difficult is how to make a measurement there and reporting it back to nature. That's a tricky thing. But I have no doubt that black holes will be at the center of much attention also in the future.
Yes. No voy a intentar traducir eso, es demasiado largo. Tengo que regatear entre traducir o dejar que Reinhard hable. Esta vez él habló. I'm saying I have to debate whether to stop you to translate or not, so I'll let you go on. I didn't say I won't translate it.
Sorry.
Not this time.
Dr. Genzel, thank you very much for being here.
These are students this evening, not.
Thank you very much for being here in Almería. I am Francisco here, professor here in Almería, electrical engineer. I'd like to go back to the unknowns, dark matter, energy, dark matter, dark energy. What do you think? What's your opinion about alternative theories like modified Newtonian dynamics? Do you think it could be an option to explain all these unknowns?
Yeah, well, okay, look, first of all, my preamble is I'm a simple experimentalist. That is, I tend to try to work hard on things where there's a chance that I will get in my lifetime an answer. To speculate about things which are interesting to speculate about, but where there's no chance, I'm not attracted to. But that's me, preamble, okay? Yes, there are many attempts to go away from the classical body of general relativity, or go beyond it, or go into more dimensions, or expand on gravity forces at low accelerations. All of this, good to have that, and when we get to it, so to speak, we should test it. And Mond, this theory which basically changes gravity on large scales, or rather small accelerations, has been tested now pretty well in the relics of the Big Bang. And I believe in that, as well as in clusters, the evidence is pretty good that it's not right. Still, there are colleagues who keep it up, and that's fine, they are entitled to do that, but I think the evidence against it has been mounting. Another interesting speculation, since we were talking about Big Bangs, okay, there's always the question, what before, yeah? And then dark energy is the dimensionality of space. And there are solutions, we know, mathematical solutions, mathematicians back there, please, which say, well, general relativity actually likes to live in much better in 11-dimensional spaces, say, that we know since Weil, and therefore could it be that while electromagnetism, etc., lives in 4D or 3D, gravity lives on 11 dimensions. If you have these other dimensions, then you have more freedom to construct, for instance, collapses between worlds, or collisions between worlds, which might look like Big Bangs. And all of this is fine, but the question is, how do you test it? This is where, again, I come back and say, I hear it, but can't do anything about it right now.
Are you happy by adding more dimensions? Are you happy by
happy? I'm not happy. No, I'm not happy about not happy.
Do you think we solve the problem by adding more dimensions?
I hear it. Okay, that's what I'm saying. I hear it, and that this proposal has been made by very serious researchers. Okay, and likewise, the whole business of going to string theory constructs for small scales of gravity is eminently interesting. The issue of the information paradox of black holes, there are all these questions, but the problem is, as long as we don't have a chance to actually measure something, then it's cheap to make predictions, okay?
Voy a traducir un poquito, porque lo que dice es, por un lado, la alternativa a la relatividad general para la materia oscura, modificando la gravedad, las predicciones concretas no concuerdan con la estructura de cúmulos de las galaxias, tal y como las medimos. Con lo cual, en este momento, la otra teoría, esa en concreto, parece que no satisface las exigencias de las observaciones. Y en todas las demás cosas especulativas, él dice que básicamente si no los puede, está bien sugerir multiversos y un montón de diferentes agujeros de gusano, cosas así, 11 dimensiones, eso está bien, pero si no los puedes comprobar midiendo, no sirve para mucho. Y es muy fácil hacer la predicción si no se puede comprobar.
Another question, there was the issue about cosmology, okay? And so it is obvious that the best instruments we have now available to us look for effects in the relics from the Big Bang which might indicate a finite universe, for instance. If that were discovered, well, that would be an indication, maybe this sort of interpretation of one universe only is perhaps fishy. But so far, we have no evidence for that.
Sí. Eso, que en la cosmología hay posibles observaciones que reflejan otros universos o lo que pasó antes de la gran explosión. Hay ideas que posiblemente van a ser comprobables, pero en este momento no se puede.
Ivan de Gracia. I have one question about antimatter. So I would like to ask about how you can test is something antimatter or matter in space. Something.
Yeah, well, okay, if the simplest case is if you have an antimatter galaxy happily living by itself, and there happens to be a matter cloud of something coming in it, you will get a hell of annihilation. And that's what has been used as an argument that at least on fairly large mixing scales there cannot be an equal or proportional matter-antimatter situation. And so then, of course, then you're forced to go back to the theoretical parts of particle physics to ask the question whether there might be an initial way to create more matter than antimatter. And I think that's what it has been so far the answer to.
Is it possible to know there is some antimatter molecules existed?
Absolutely, from the spectroscopy. Yeah, I think from the radiation signatures, if you had significant amounts of antimatter, you see it. I mean, we can see it in any case, around the Earth. I mean, it's being produced from time to time, so it's not that there is no antimatter.
But I heard about small molecules like hydrogen antimatter, but there is maybe bigger mass molecules of antimatter.
Well, there is no evidence, but people are looking.
People are looking, yeah.
Thank you.
Yeah. You never believe what they tell you. That's clear. But on the other hand, I also said the day is only 36 hours. And so then...
Tenemos que cortar, porque si no es una comida.
Bueno, yo lamento deciros que vamos a ir abreviando. Quizá tenemos una preguntilla, dos preguntas y no más, ¿de acuerdo? Había pendiente, lo digo porque tenemos que ya ir abreviando.
Hello, thank you for being here. As I am a big fan of physics in general, even though I am studying math. So my question is, do you think gravitational waves can provide us more information about the universe that is not accessible with light or other radiation?
Absolutely. Yeah, no, I think, if I look at the next 20 years, then I would say one very ambitious but doable mission stands out in my mind. and that's LISA, the space interferometer gravitational wave instrument of ESA and probably ESA plus NASA. I think in the end the two have to work together. It's extremely ambitious because you have to have satellites which are 2.5 million kilometers away sending lasers to each other, and then basically seeing relatively low frequency or long wavelength distortions due to large scales either in the early universe or, for instance, if you have a stellar black hole spiraling into a massive black hole or two massive black holes spiraling into each other. There's a whole world out there which I would love to see. This is going to be, however, when I look at the flowers from below, but you young people, that is a wonderful future. Do it.
Sí, el futuro. 20 años de trabajo con LISA, que es el proyecto de la Agencia Espacial Europea, probablemente al final con NASA, que va a profundizar muchísimo en nuestro entendimiento de objetos que causan ondas gravitacionales. Por ejemplo, ondas en el Big Bang o ondas que ocurren por un agujero negro pequeño entrando en un supermasivo. Y eso es un campo muy emocionante para gente como ustedes, para gente de vuestra edad, si está atraída por la ciencia.
Hi everyone, thank you for the opportunity. My question is, although most of the stars in the Milky Way are in the main disk, what is the origin of these stars out of it orbiting around the central supermassive black hole?
Okay, well, there were of course different phases of our Milky Way, and we can see these earlier phases, so to speak, by looking at galaxies at large distances. Right? So there we see what happened in our Milky Way in the past by looking far away. And so in the early universe, galaxies which formed were different in that they had much more gas. Stars were forming at much higher rates. I mean, our galaxy now, Milky Way is forming 2 stars per year, roughly, in the entire Milky Way, 100,000 light years across. Whilst 10 billion years ago, a similar mass galaxy formed 100 to 200 times more stars per time. And so that meant there was much more energy produced per volume. And that meant that the systems were much thicker. Okay, they were much less flattened into a thin disk. So this early phase we can see both in these distant galaxies, but also as relics in our own galaxy. So we can see a population of stars, the thick disk population, which goes back to that early epoch. It's likely that there were also effects due to interactions between galaxies. And when that happens, it can be really destructive and also spectacular. Our galaxy probably did not so far have such a traffic jam collision, but it will have one in 2 billion years. So if you're around, be sure to get insurance. But I mean, there's a lot of change in these processes over time.
Bueno, él está hablando de los cambios que han ocurrido en el universo. Las galaxias cerca del principio, una galaxia del mismo tamaño que la Vía Láctea, estaba produciendo 1000 veces más estrellas por unidad de tiempo que la galaxia actual. Bueno, I think I lost the third point. We were talking about
the thick disk.
Y en ese caso, las galaxias tenían discos que eran gruesos, el disco de las galaxias modernas, actuales, es muy fino, pero hay componentes que se llaman disco grueso. Y cuanto más hacia atrás, más discos gruesos. Muchas diferencias entre entre galaxias. Esas son cosas que el James Webb, por ejemplo, está explorando.
And find the interruptions.
Y al final, la interacción entre galaxia y galaxia, que también produce muchas estrellas más. Hay galaxias que interactúan todavía ahora y son zonas de intensa formación estelar que se pueden estudiar. Sorry, I was distracted.
Okay. Thank you very much, Dr. Genzel, for your very interesting colloquium with your students, with people. Dr. Beckman, thank you very much for your very clear translation. And thank you to the audience for being here and attending this colloquium. I remember you that this evening we have another meeting with Dr. Genzel at Teatro Apollo in Almería, the city center.